During this video, we're going to be reviewing the experiment that is the first order measurement system. We are looking at temperature instruments and their first order response to characterize the time constant as a first derivative term in the dynamic response of the instrument. So this is being done in the context of an application focused on measuring ice rink ice, where we're trying to design the measurement system for a little rover that can go around the ice and quickly measure depth and ice temperature. So we're doing some initial analysis of behavior of different instruments in order to choose one for a design that would be end mounted on a cantilevered beam on a little rover that could go around the ice and do the job faster than others. So this is in the context of measurement system behavior, where we're characterizing measurement systems by their dynamic response using a lumped parameter model. And so we have differential equations that include typically up to second order terms and input and output. This one is a first order term. And so we're looking at the relationship between the input F and the output Y with initial conditions at the beginning of the experiment. So when we look at first order systems, we start to cross off terms in that model, and we get down to a simple first order derivative where we have tau times the first derivative of time, y dot, plus y equals k, some sensitivity, times input f. And this is a classic model for the behavior of a thermometer, which does typically respond as a function of time based on its design and characteristics that typically is modeled as an exponential decay in time. We compute a parameter called the error fraction by monitoring the signal, the response temperature as a function of time, where we keep track of the actual temperature, the time, the final temperature, we call it infinity. The initial temperature is also part of that. And we model that to e to the minus t over tau. When we take the log of the gamma, the error fraction, we essentially get a straight line where the slope is minus 1 over tau. We can solve the slope and get back to tau. So that's what this experiment is about. Specifically, we have some temperature instruments here that we're going to plunge into an ice or a snow bath in a beaker. And we're going to track those over time. The best way to do this is actually to record a video with your phone. You can do it if you are good at videography. You can capture all of the instruments' response all at the same time, or you can actually run this experiment with each different temperature instrument one at a time to really be able to see the response over time. It does require some post video processing to go back through and record the time and temperature at various steps. Now we have little timers as well on the benches here that you can use that can actually record time much more accurately. So if you use that, you can include that in your video as well, and you'll get a smaller resolution of time than most likely your phone camera. So there's a basic procedure here, and effectively what we're doing is a step response or an impulse response experiment. We're going to subject the system to an immediate change going from room temperature to instantaneous plunge into ice, and then we're going to see how that system responds. There will be a steady state response and a transient response. We're mainly interested in the transient response, the part of the response that changes with time. And in the error fraction version of that data, we see this nice exponential decay. A temperature instrument that responds very quickly will immediately draw down to the zero axis here and then go over. That'll have a lower time constant. Something that takes its time, perhaps like a bulb thermometer, will have a longer response. Depending on the use case, that really matters. Oftentimes we can take some time to measure something and wait. Other times we really need an instantaneous response. And typically the response characteristics are set in the specifications of an instrument. Okay, the particular instruments that we're going to use, we have a quick response pocket thermometer. We have a water-resistant digital pocket thermometer, a pocket dial thermometer, the kind of thing that you would use typically in a kitchen application. And then we have a multimeter with a thermocouple, type K thermocouple installed on it. We're using a weighted base holder, the same one we used for the granite surface for our height gauge test with the previous lab. And then we also have a timer here as well. So this is related to the assignment, and the step-by-step instructions are listed here. Now, I'm not going to go through these step by step. I'm just going to kind of cover the setup so that you can run this on your own. Make sure that you follow these step by step, and then particularly follow the analysis steps at the end here. So in the textbook, this is shown here under Chapter 3, Measurement System Dynamic Response, which discusses different types of special cases, including a first order response. And the first order response, the classic one that we're looking at, is the step input. And so if you want to read about the details of that, this is in Chapter 3 of the textbook. Another type of test is one in which we actually provide not just a step response, but more of a periodic, simple periodic response. We're not going to do that part today. We're really going to focus on just the time constant from a step response. So that's the chapter, that's the assignment, and those are the slides. So I've turned the camera around so we can see the basic benchtop setup. We have a beaker of water, our surface table here. We also have our mount where we have different instruments mounted. The thermometer is a glass bulb thermometer. And so appreciate you being careful with that. Try not to break it, especially when moving in and out with the beaker. So you can see capillary action based thermometer here, traditional thermometer, and its case allows it to kind of lock in like that and then be stored like that. We also have a digital thermometer that's a commercial kitchen thermometer typically, and it has appropriate specifications on the back. And you'll have to read those to figure out exactly what's going on in there, what type of temperature measurement it is. And there's a temperature well where the actual sensor is down in the tip here. And so you can, has a battery, you turn it on and off with the button here. We also have classic dial thermometer. Okay, so also an analog response, not digital, similar to the capillary bulb thermometer. And we have a digital multimeter where we have a thermocouple installed. So the thermocouple we can measure by moving over to the temperature knob here. You can see temperature and degrees C. If you want it in different units, Fahrenheit, you can press right there. So C right here. So there is an ice chest that's in the lab right here. Typically has ice in it and an ice tray. Okay, and so typically we'll be adding the ice each time. Try not to make too much of a mess, and then I'd appreciate if you would fill back up the ice trays when they're done.
Sorry, what are you looking for? Are you looking for the bag in the big box? Okay, amazing. I'm so sorry. I was.
That's good enough. We'll fill that up later, and we'll try to clean up some of that mess there. So there's also a timer. The timer has some instructions in a little box here. I'm not actually going to use it right now, but the gist is that we're really going to try to set up a camera with a phone so that we've got our ice bath right here. We want to get all of these turned on and reading and about the right same height, and then set them up visually so that we can actually see all this. So the experiment is really simple. With a camera on, you're going to simply record a video of these guys as you plunge them into water. One important thing is to make sure they're all at a steady state room temperature for a certain period of time where the temperature is not changing. And then you want to plunge them in and record the time it takes for them to come to a stable temperature of the ice bath. Now, I just put the ice in, and so it should be pretty close to ice temperature, but at the end of the day, the actual temperature doesn't matter. It's that we can measure the response curve as it goes down. Turn on the video, your camera, and then little by little, we're going to get closer, and then best we can without damaging anything, we'll just do a quick plunge, and we're videoing all of those guys, and then we wait till they respond. Some of them I can see the bulb thermometer just on the top of the ice here. This guy's little by little coming to a steady temperature, and this guy's continuing to move the dial indicator here. And this guy continues to get down close to zero, and then it's basically, that's it. This guy is around 0.4. And the dial thermometer is continuing to go down little by little. So after the experiment's complete, after they come to a steady temperature, stop the video, and then you can pick this back up. Try to keep it so they're all in a position where they're not going to hit the beaker. Turn off the meter, turn off the timer, and then get ready for post-processing. You want to clean up the ice and clean up the station, and then pretty much just leave it like that. As far as your data, you can expect to have, I've drawn it in kind of purple here with a couple different, 2 different sensors here, temperature over time, okay, and you'll end up tabulating that data as you go, computing error fraction, and you can do some of the analysis in Excel if you'd like, and so you can get temperature, time and temperature for the thermocouple, time and temperature for the thermometer, for example, error fraction, and continue on out. You can use a Linus function or whatever you want to compute the slope. From the slope, you can compute the time constant tau, which has units of seconds. It's important to note that. If you want to plot it in Excel, you can do that as well. And you can plot this different ways, including log scale, if you like. And that should be that as far as the experiment. So if you have any questions, let me know. And I think that's about all you need.